You'll now learn about scaling Amazon Elastic Compute Cloud, or Amazon EC2, instances. In a traditional data center environment, the scalability of a system is typically bound by your hardware. If you take the example of a tax preparation business in the United States, U.S. taxpayers must file their taxes by April 15th. Online tax preparation companies know that they will experience a steady flow of traffic starting near the middle of January, and the traffic peaks close to the April 15 deadline. In a data center scenario, the need to anticipate this 4-month period of heavy use means that they must provision enough physical servers to handle the expected load. But what happens to those servers during the rest of the year? They probably sit there idle in the data center. In the cloud, because computing power is a programmatic resource, you can take a more flexible approach to the issue of scaling. You can create new EC2 instances before peak periods that you're aware of in a business cycle, such as the tax filing deadlines. You can use monitoring to programmatically scale out servers when the critical resources become constrained, using metrics like average CPU utilization across your fleet. And you can automatically scale in the number of resources that are used during peak times when demand for the business returns to the baseline. In other words, you pay for the resources you need when you actually need them. What is needed to implement a system like this? You will see how several AWS services can be used together to create a scalable, on-demand architecture. You're now going to learn about Route 53, ELB, and auto-scaling groups. Amazon Route 53 is a highly available and scalable cloud domain name system, or DNS service. It's been designed to give developers and businesses a reliable way to route end users to internet applications by doing the job of translating names like www.example.com into the numeric IP addresses that computers use to connect to each other, like 192.0.2.1. It often makes sense to configure Route 53 entries to actually point to Elastic Load Balancing load balancers. Elastic Load Balancing, or ELB, is a service that automatically distributes incoming application traffic across multiple different targets, which could be EC2 instances, containers, IP addresses, and even AWS Lambda functions. It can handle a varying load of your application traffic across a single availability zone or multiple availability zones. It provides 3 types of load balancers that will offer high availability, automatic scaling, and security to help support making applications fault tolerant. And ELB load balancers are often configured to point to auto-scaling groups. Each auto-scaling group contains a collection of EC2 instances that share similar characteristics and are treated together as a logical grouping for the purposes of scaling and, of course, management. They help to maintain application availability, and they also enable you to dynamically scale capacity up or down according to conditions that you define. Here's a more detailed look at ELB. Most web application deployments on AWS use ELB. ELB routes the client request across multiple EC2 instances, or ECS, Amazon Elastic Container Service, the containers that run your web application. This way, you can balance the load and make sure that no single instance gets overloaded. You can also use cross-zone load balancing. This reduces the need to maintain multiple instances in one availability zone and provides the added benefits of fault tolerance in helping reduce imbalances in the utilization of the back-end instances. You can set this up by enabling cross-zone load balancing by default on all application load balancers and using health checks to shift traffic as needed. And it's important to know that the load balancer absorbs the impact of DNS caching, and there is no additional bandwidth charge for cross-zone traffic. When you configure an ELB load balancer, which is part of the Amazon EC2 service in the AWS Management Console, you can choose from 3 different types of load balancers: application load balancers, network load balancers, or classic load balancers. Now you will learn about each one in more detail. First, an application load balancer supports content-based routing, which is one of its main strengths, and it can also support applications that run in containers. Here are a few details. First, application load balancers support the WebSockets and HTTP2 Open Standards Protocol, and they can give additional visibility into the health of the target instances and the containers. This means that websites and mobile apps that run in the containers or on EC2 instances will benefit from the use of application load balancers. This type of load balancer works well for the advanced load balancing of HTTP and HTTPS traffic because of features like advanced request routing that supports modern application architectures, specifically microservices and container-based applications. We generally recommend using application load balancers for all other use cases that involve Amazon Virtual Private Cloud or Amazon VPC. If you want more details about application load balancers, including container support, search for using static IP addresses for application load balancers in the AWS documentation. The network load balancer has a particular strength in that it is designed to handle tens of millions of requests per second, while maintaining high throughput at ultra-low latency, with little effort on the part of the user. Here are the key features of the network load balancer. First, network load balancers route connections to targets, which are EC2 instances, containers, and IP addresses, based on IP protocol data. You can use the same API to programmatically control both network load balancers and application load balancers, including full programmatic control of target groups and targets. A network load balancer is ideal for load balancing TCP traffic, and the network load balancer has been optimized to handle sudden and volatile traffic patterns while presenting a single static IP address per availability zone. We recommend using network load balancers to balance TCP traffic in a VPC or when your application requires the load balancer to have a static IP address. The classic load balancer provides basic load balancing across EC2 instances. It can operate at both the request level and connection level. Classic load balancers are intended for applications that were built in the EC2 Classic network, which was before the VPC. Be aware that EC2 Classic networks are not available for accounts that were created after 2013. Classic load balancers do support VPC use cases, but you should consider using application load balancers or network load balancers instead. For a side-by-side comparison of the features for the three load balancers, you can search for Elastic Load Balancing Comparison on the AWS website. You'll now learn more about some ELB features. A load balancer is designed to distribute workloads across multiple compute resources like EC2 instances, containers, or Lambda functions. You can configure load balancers in the EC2 service area in the AWS Management Console. You can also configure them programmatically with the AWS Command Line Interface, or AWS CLI, or by using the AWS Software Development Kits, or SDKs. Here are some of the key features. First, load balancers can give you high availability by distributing traffic across multiple targets, including EC2 instances, containers, and IP addresses, either in a single availability zone or across multiple availability zones. Next, load balancers can also be configured to detect unhealthy targets and stop sending traffic to them. They can then spread the load across the remaining healthy targets. You can also create and manage security groups that are associated with load balancers, and you can create internet-facing or internal non-public load balancers. Note that load balancers include integrated certificate management and decryption with Secure Sockets Layer, or SSL. This means you can centrally manage the SSL settings of the load balancer and offload CPU-intensive work from your applications. You can also load balance HTTP and HTTPS applications for features that are specific to Layer 7. When you hear Layer 7, it refers to the application layer in the Open Systems Interconnection, or OSI model. You can also choose to use strict Layer 4 load balancing for applications that rely on TCP. Layer 4 is the transport layer in the OSI model. And finally, load balancers provide integration with Amazon CloudWatch metrics and request tracing, and this enables application performance monitoring in real time. Before you start using your application load balancer, you must add one or more listeners. We will now define a listener. A listener is a process that checks for a connection request from a client to an instance, and it uses the protocol and port that you specify. The listener rules that you define also then determine how the load balancer routes traffic from connecting clients to one or more targets or target groups. Overall, a load balancer serves as the single point of contact for clients. When you create each listener rule, you specify a target group and conditions. Targets are organized into target groups. Each target group is used for routing requests to one or more registered targets, such as EC2 instances or ECS container instances. You can also configure health checks on an individual target group. When you specify a target group in a listener rule for your load balancer, health checks are performed on all the targets that are registered to the target group. For more information, you can search for Elastic Load Balancing Introduction in the AWS documentation. Here's an example application load balancer for the example.com website. The load balancer serves as the single point of contact for all clients. It's distributing incoming application traffic across the multiple targets. Be aware that an application load balancer can have more than one listener. In the example, you can see there are two listeners. Each listener checks for connection requests from the clients using the protocol and port that you configured. And the listener then forwards requests to one or more target groups based on the rules defined. Each rule specifies a target group, a condition, and a priority. When the condition is met, the traffic is forwarded to that target group. You must define a default rule for each listener. You can also add rules that specify different target groups based on the content of the request, and this is known as content-based routing. Regarding the target groups, each target group uses the protocol and port number that you specify to route requests to one or more of the registered targets, like EC2 instances. It is possible and sometimes desirable, especially with containers, to register a target with multiple target groups. You can configure health checks on an individual target group. When you specify a target group in a listener rule for your load balancer, health checks are performed on all targets that are registered to that target group. To reiterate, you can see that each listener contains a default rule, which is mandatory, and one listener contains another rule that routes requests to a different target group. As the graphic shows, you can register a target with multiple target groups. To show how request-based routing works, here is a single application load balancer that is configured with 3 rules. The design helps show the functionality of each segment or target group, which is based on the URL that is requested by the client. You can see that clients requesting the www.example.com/orders page are routed to one set of EC2 instances. And a client that requests the www.example.com/images page is routed to other EC2 instances. And so are clients requesting the /registration path. Now, here's an example of the AWS CLI command you would use to create a load balancer. When you issue the command, 2 subnets must be specified for the load balancer that are not from the same availability zone. The command returns a JavaScript object notation or JSON document that lists the load balancer ARN, which is the Amazon resource name, and the DNS name with some additional metadata about the load balancer, including the name and load balancer type. After you create your load balancer, you can use this AWS CLI command to create a target group. Remember that you must specify the VPC where your EC2 instances are running. After you create the target group, you could use the AWS CLI to register the EC2 instances in the group, and you must provide the target group ARN and the EC2 instance IDs. And finally, you could use the create listener command to register the target group with the load balancer. This command requires the load balancer ARN and target group ARN parameters. After the load balancer is created, you could use the describe target health command to check or validate the configuration. And this means that you must supply the target group ARN. Thanks for watching. See you in the next video. Welcome back. You're now going to learn about Amazon EC2 autoscaling. Amazon EC2 autoscaling helps you maintain application availability. It enables you to automatically add or remove EC2 instances according to various conditions you define. For example, you could configure Amazon EC2 autoscaling to terminate EC2 instances that fail health checks, and then to launch new instances to replace them. And you can create user-defined policies that use Amazon CloudWatch to trigger when to add or remove EC2 instances based on conditions like the average CPU utilization of your EC2 fleet. If the load changes are predictable, you could set a schedule to help bring resources online ahead of time, and you can specify allowable fluctuations for the scaling activities within windows that you define. The main overall advantage is to be able to automatically scale out to meet demand and to scale in again to reduce costs when demand is lower. The process for configuring Amazon EC2 autoscaling involves first creating a launch configuration before the actual autoscaling group is created. To create the launch configuration, you specify roles through AWS Identity and Access Management, or IAM. You also specify the security groups, storage, instance type, user data, key pairs, and so on. These requirements are similar to launching an EC2 instance, but you don't specify a VPC or subnet for the instances. This information will come from the autoscaling group itself. You must pay careful attention to one particular configuration option in the launch configuration, which is whether to automatically assign a public IP address to each new instance. But you don't need to select this option if your instance will be launched in a private subnet behind a public load balancer, for example. There are two main ways to trigger changes to an autoscaling group. First, you could define a scaling policy that's either going to scale out or scale in based on a CloudWatch alarm. Then you define a CloudWatch alarm, like the average CPU utilization is greater than 50% for 2 minutes, and then have the alarm call the autoscaling policy. The policy will then specify one of two options, like adding or removing a fixed number of instances, or adjusting the number of instances as a percentage of the desired capacity for the group. Second, you can define a scheduled action. A scheduled action sets a new desired capacity value at a specific time. You can specify it to trigger on a specific date and time, or to recur at specific times during a week, a month, or a year. This can be a good way to pre-warm capacity in response to anticipated traffic spikes like sales, year-end processing, or any predictable workload spikes. Amazon EC2 autoscaling tracks the health state of instances and can then terminate instances that are marked as unhealthy. You could use it to help ensure that the instances in the group are functioning properly. By default, Amazon EC2 autoscaling uses EC2 instant status checks. If an autoscaling group is behind a load balancer, either the load balancer's instant checks or the Amazon EC2 instance checks are used for health monitoring. But you could use external scripts to trigger recycling of an instance at any time by invoking the AWS autoscaling set instance health command. If you want more information about instant status checks, search for monitoring system status checks in the AWS documentation. With each autoscaling group, you control when it adds instances to your architecture, which is called scaling out. You also control when it removes instances from your architecture, which is called scaling in. You can scale the size of your group manually by attaching and detaching instances, or you can automate the process by using a scaling policy. There is something called a default termination policy, which is designed to help ensure that the instances span availability zones evenly for high availability. And the default termination policy is typically sufficient for most situations. But you can replace the default policy with a customized one. For example, you could define a custom termination policy to decide which instances to terminate first during a scale-in event. You can use the Amazon EC2 autoscaling API, terminate instance in autoscaling group action, to terminate a particular instance and to decrease the desired group size. For example, you might choose to always terminate the instance with the fewest user sessions. After you've determined the instance ID, the terminate instance in autoscaling group can be called, and the instance ID can be passed in as a parameter. For more information about this, search for autoscale instance termination in the AWS documentation. You can customize the termination policy so that if one availability zone has more instances than the other availability zones in the group, Amazon EC2 autoscaling applies your termination policy to the instances from the imbalanced availability zone. If the availability zones used by the group are balanced, then Amazon EC2 autoscaling applies the termination policy across all of the availability zones in the group. There are 4 different types of custom termination policy. The first one terminates either the oldest or newest instances in the group. You might want to terminate the oldest instances if you're upgrading the instances to a new EC2 instance type, for example. Or you might terminate the newest instance in the group when you're testing a new launch configuration but don't want to keep it in production. You could also terminate instances with the oldest launch configuration. You might do this if you are updating a group and phasing out the instances from a previous configuration. Last, you can have a policy that terminates instances that are closest to the next billing hour. This is a good way to maximize the use of your instances and help manage your EC2 usage costs. It's also worth being aware of Amazon EC2 autoscaling health checks because you could create a steady state group that helps ensure that a single instance is always running by replacing it if required. This can be useful if you have a network address translation or NAT server and you do not want it to be a single point of failure in a standard public-private subnet architecture. You can also scale based on a schedule in response to predictable load changes, as seen here. For example, you notice that every week the traffic to your web application starts to increase on Wednesday. Traffic stays high on Thursday and then starts to decrease on Friday. You will soon learn the steps to configure an auto-scaling group based on a schedule. You can configure automatic scaling to be dynamic. For example, you have a web application that currently runs on 3 instances. You don't want the CPU utilization of the auto-scaling group to exceed 70% for more than 2 minutes. You can configure the auto-scaling group to scale automatically to meet this need. Here's a look at how the policy type determines how the scaling action is performed. Amazon EC2 autoscaling supports 3 types of scaling policies. First, you can use target tracking scaling, which increases or decreases the current capacity of the group based on a target value of your chosen metric. For example, aim to keep group CPU average at 65%. Next, you can have step scaling. Step scaling increases or decreases the current capacity of the group based on a set of tiered scaling adjustments, which are known as step adjustments. And finally, simple scaling increases or decreases current capacity of the group based on a single scaling adjustment. You also have predictive scaling. Predictive scaling uses machine learning models to predict your expected traffic and Amazon EC2 usage, including daily and weekly patterns. It uses data collected from your actual EC2 usage and data points that are drawn from our own observations. The model itself needs historical data from at least 1 day to start making predictions, and it's re-evaluated every 24 hours to create a forecast for the next 48 hours. Here are some key points to consider. First, predictive scaling predicts future traffic based on daily and weekly trends, including regularly occurring spikes, so that it can provision the predicted number of EC2 instances before anticipated changes. It also reduces the need to manually adjust Amazon EC2 autoscaling parameters over time, which helps make Amazon EC2 autoscaling simpler to configure and consume as a user. Be aware it appears under the AWS autoscaling page in the management console, not the EC2 area. So to get started, you navigate to the AWS autoscaling page and create a scaling plan for EC2 resources that includes predictive scaling. After it's enabled, you can visualize the forecasted traffic and the generated scaling actions. You can combine predictive scaling alongside dynamic scaling. Keep in mind that it works by forecasting load and scheduling a minimum capacity, but dynamic scaling uses target tracking to adjust resources that help keep a designated CloudWatch metric to a specific target. Ultimately, the 2 models can work well together because the scheduled minimum capacity is already set by predictive scaling. In conclusion, predictive scaling is a good choice for websites and applications that typically experience periodic traffic spikes. It's not really designed to help in situations where spikes in the load are not cyclic or predictable. You'll now learn about avoiding thrashing. When there is excessive use of a computer's virtual memory, the computer cannot service the resource needs of running applications, and the condition is known as thrashing. It's a good analog to when instances are removed and added, or added and removed in too quick of a succession because of automatic scaling. One way to avoid thrashing is to trigger alarm actions for actual sustained state changes only. That is, for state changes that have been maintained for a reasonable period of time. It's helpful to know the Amazon EC2 autoscaling cooldown period setting because it helps ensure that autoscaling doesn't launch or terminate instances before the previous scaling activity takes effect. When you manually scale your autoscaling group, the default option is to not wait for the cooldown period, but you can override the default option and observe the cooldown period. Likewise, if an instance becomes unhealthy, Amazon EC2 autoscaling doesn't wait for the cooldown period to complete before it replaces the unhealthy instance. Amazon EC2 autoscaling supports default cooldown periods and scaling specific cooldown periods. However, remember that cooldown periods are supported when you use simple scaling policies, but not when you use target tracking policies, step scaling policies, or scheduled scaling. You can also specify the number of seconds it takes for a newly launched instance to warm up. An instance is not counted towards the aggregated metrics of the group until its specified warm-up time is expired. When scaling out, AWS does not consider instances that are warming up as a part of the current capacity of the group, so multiple alarm breaches that fall in the range of the same step adjustment only result in a single scaling activity. This helps ensure that Amazon EC2 autoscaling doesn't add more instances than you need. Also remember that in some cases, you might want to perform an action manually before automatic scaling takes place. Lifecycle hooks give you this flexibility. Here are some examples of scale out and scale in sequences. Look at the scale out example first. Here, Amazon EC2 autoscaling launches an instance, sends a pre-configured notification to a person or application. It then takes no further action because the user or script must install any software and then add the instance to the group. In the scale in example, the Amazon EC2 autoscaling lifecycle hook removes an instance from the group and then sends a notification. Now, when the user or programmed action receives the notification, it performs an action on the instance before it terminates the instance. A good example might be retrieving the instance's logs. If you want more information about the Amazon EC2 autoscaling lifecycle, search for Autoscaling Group Lifecycle in the AWS documentation. Thanks for watching. See you in the next video. It's now time to review the module and wrap up with a quick discussion of a practice exam certification question. In summary, you learned how to describe the features of elastic load balancing and the different types of load balancers. You also learned about Amazon EC2 autoscaling and how to configure Route 53 for several different routing configurations. Well done and great work. You'll now look at a sample certification question. Take a minute now to review this sample question that could be on a certification exam. And now, review this sample scenario and look for any keywords that will help you identify what the correct answer is. Here, the keywords in the scenario now are highlighted. Here's a look at the answer options. Keeping the keywords in mind, look at the answer options and try to rule them out based on what you see in the highlighted words. The best solution in this case is an application load balancer. Now it's time to complete the Module 4 guided lab, Configure EC2 Autoscaling. Here you will also complete the Module 4 challenge lab, Route 53 failover routing. And that's it. Thanks for watching and see you in the next module. Hello and welcome. You are now going to learn about containers and serverless computing on Amazon Web Services, or AWS. In this module, you'll get a general overview of containers and also learn about the AWS services for containers and serverless computing. You'll start by reviewing AWS Lambda, which is a compute service for running your code without needing to provision any infrastructure. Next, you'll review Amazon API Gateway, which is a service for exposing REST APIs that communicate with back-end HTTP endpoints like AWS Lambda. Then you will spend some time learning about container services in general before you learn about the 3 different AWS services that you can use with containers. These services are Amazon Elastic Container Service, which is also known as Amazon ECS, AWS Fargate, and Amazon Elastic Kubernetes Service, or Amazon EKS. Finally, you'll review how you can use AWS step functions to coordinate AWS services into a serverless workflow. At the end of this module, you will be able to explain the purpose and function of AWS Lambda and deploy a simple Lambda function. You'll also be able to describe the purpose and function of APIs, including REST APIs. You'll be able to explain the benefits of the Amazon API Gateway and how to use and operate it with REST APIs. You'll also be able to describe what containers are and to distinguish between the different AWS services that work with containers. And finally, you'll be able to explain the purpose of AWS step functions. Okay, you're ready to go and get started.